Good evening, everyone. So I think we can slowly start. Today we have a pleasure to attend the talk by Professor Sepehr Assadi, who recently joined Cheriton School of Computer Science as associate professor. Sepehr obtained his bachelor degree from Sharif University. He received his PhD from University of Pennsylvania, and then he spent postdoctoral as a postdoctoral fellow some time at Princeton University. He received several awards. Some of them are Sloan Research Fellowship, NSF Early Career Development Research Award. And today we have a pleasure to listen to the talk on sparsifications for matching and streaming.
All right, perfect. Thank you so much. You can all hear me, yes? Good. All right. So thank you, everyone, for coming to the talk, and thank you for the organizer for inviting me. So I'm going to talk on the Blackboard. I'd like that a bit more. So, and also it means it's a Blackboard talk. Stop me at any point, ask questions. Good. So before getting to this topic, I wanted to very quickly, this is my first time here, so let me do a very quick introduction for myself also. Most of my research is in theoretical computer science. All of my research is in theoretical computer science. Most of it is on algorithm and complexity for quote-unquote modern models of computation. Usually you can put that all on the umbrella of sublinear algorithms and lower bounds. And some of the topics that I've been very interested in recent years, let me write here, is graph coloring, things like omega, delta, chi paradigm, extremal graph theory, which is, like for instance, a question here I'm very interested in is understanding Zemeredi graphs. And that's my most favorite topic in the last couple of years have been information theory and communication complexity. The reason I'm listing this thing is that I was thinking about what topic to pick and come and give a talk here, and I had a hard time figuring out, especially between graph coloring and information theory. And then I realized, okay, this is Tutte Colloquium, I would like to talk about matching. So decided to not do any of these things and talk about matching. I'm just putting them here. If you wanted to talk about those things, I'd be very happy to talk later. Good. So the rest of the talk has nothing to do with this. It's only going to be about matchings. Okay, good. And it's going to be one other caveat. This is a result, it's a very recent result in SOSA conference. It's a symposium on simplicity for algorithms. The whole point of this talk is I want to show you something very, very simple. Like usually you'll see these theory talks that at some point in the talk you're going to try to woo the audience by doing something super technical. That's never going to happen in this talk, okay? Like the whole point is to be very simple. So if any point I said something which even sounded like it remotely complicated, stop me, ask questions. I want to show you the entire proof of this result here, or at least the easier case for bipartite matchings. Okay, good. So with that, let's start. So the object we are going to look at today are maximum weight matchings. As a quick definition, a matching in a graph is just a collection of vertices that do not share any edges. So if I have a graph like this, 2, 7, 6, 1. So I may have a graph that looks like this. It doesn't need to be bipartite necessarily. This is a general graph. It has a triangle. Okay? And I want to find a maximum weight set of edges such that they do not share any vertices. So what do you think is the answer here? Like, what is the maximum weight I can get in this graph? It's 8. No, it seems like the easy choice would have been to just pick 7, but the moment you pick 7, you block all the other edges. Okay, so it's better that you pick 6 and 2, and you get 8. Okay, good. This is a very fundamental problem. People have studied different variants of this problem in various settings from ages ago. Maybe one of the nice results here, like it's from Koenig from 1916. It's one of the earliest examples of combinatorial duality that I know, that shows size of a maximum matching in a bipartite graph is equal to the size of the minimum vertex cover in a bipartite graph. Okay. Then we have a result like Todd from 1947, and then Berg. This is the Todd-Berg formula that tells you how you can characterize size of maximum matching in a graph, for instance. And perhaps one last thing here will be Edmond's algorithm from 1967. 5. If you've heard of complexity class P or polynomial time algorithms, that started with Edmonds designing an algorithm for non-bipartite matching, and then say that polynomial time seems to be the right measure of looking at, like, consider efficiency of algorithms. And why do I say this result is that matching is a nice problem on its own. It has applications, etc. But I think the main thing is that it's a very nice problem as a lens to look at algorithmic problems as a whole, basically. It's a good way of looking at trying new algorithmic techniques for solving the problem, and like developing lots of both algorithmic combinatorial techniques that you first apply them to matching, and then you can generalize them to lots of other problems. In some sense, I think another problem that is similar to this is set cover when you're designing approximation algorithms, for instance. Good. So what are we talking about today? I want to look at so there are algorithms that solve this problem. We know them. I'm not talking about those here. We want to look at a particular scenario that we want to solve matching. And the setup is something like this. Let me first say, suppose I'll come and tell you, look, I'll give you this oracle. It can, for instance, find an approximate matching for you. It can find a 1 minus epsilon approximate matching for you in an efficient manner. Okay, so I'll give you an algorithm that does this. The only restriction is that this algorithm only works on sparse graphs. Okay, so you can only run such an algorithm if you have a sparse graph. If your graph is very dense, that algorithm is not designed for it. Okay, does this make sense? So, in fact, if I take a step back before, it's about, topic of this talk about is notion of a sparsification. I have a dense graph. I want to solve matching over it. Instead of taking any of the algorithms that I have and run it directly on the dense graph, which might not be efficient for various reasons, I want to first try to make my graph sparser, okay, by some computation which is not as heavy as finding the matching itself. Like, I want to sparsify my graph in an easy way, and then solve my matching problem only on the sparser graph. Okay, as an approach, does this make sense? Like, you may have seen this, for instance, in cut sparsifiers. If you want to find a minimum cut of your graph, what you can do is that you can first find a cut sparsifier of the graph, and then solve your minimum cut problem on the cut sparsifier instead. Okay? Or if you want to find shortest path, you can do a tree embedding, or you can find a spanner first, and then do the computation on a sparser graph. Okay. The question is, can you do the same thing for matching as well? Okay. And, okay, I said I will not talk about this thing, but let me just mention briefly. Rosa-Zameridi graphs are, so the answer to that question, like in a vanilla sense, is no. It's not easy to take an arbitrary graph, sparsify it, and maintain large matchings inside it. Okay, and you can formalize that. there are some caveats here. I mean, of course, you can take the graph and pick its maximum matching. It's as sparse as it gets. Okay, so let me not get into it. Okay, but what I want to do here is that maybe I cannot do this thing in one shot. Maybe I cannot look at my graph, do something easy and sparsify it right away, and then solve the matching over it. Maybe I can do this in a couple of iterations. What it means is that I take my graph, I sparsify it first, and I compute a matching from it. And then I realize, look, this matching is not as good as I hoped for. Okay? And then I'll go back and consult my original graph. Maybe I should sparsify it with this extra knowledge a bit better. Okay? And then I'll get another sparse graph. I compute a matching from it. And then I'll go back and consult in my original graph again. Okay? And I want to do this thing very few number of times. Does the setup make sense? Okay. I will formalize it a bit more, but the idea behind this is I want to only do my heavy computation on a sparse graph, okay? And spend the rest of my time just trying to do a simple computation that make my graph sparse. Okay? So let's look at it this way. Let's say I have an algorithm. In fact, maybe I can just do it in the model itself that I want to talk about. Let's talk about this model. The reason I was hesitating a bit to even jump into a streaming model and talk about it, what I'm going to talk about has almost nothing to do even with the streaming that much. We are not going to use that much power of the streaming model. I'm going to do something very basic there. But let's define the model anyway. So let's say you have a graph G, V and E. Let's say vertices are this set. So the vertices are known. There is nothing unknown about them. They're numbers 1 to n. And then the edges are written in some arbitrary order somewhere. Yeah. So I have this sequence of edges written somewhere. Okay? And to model the fact that I don't want to do heavy computation on this graph, I'm going to only allow myself to read these edges in a sequential order. Okay? So I'm only allowed to make a pass from left to right and just read these edges. Okay? And while I'm doing that, I have one other restriction. So my memory is to be proportional, let's say, roughly n. The memory that I have available to me has its size is proportional to my number of vertices. It's not large enough for me to make this pass and store all of it inside my memory and then solve the problem. Does it make sense? Okay, good.
So sparse is going to mean linear?
Yes, like, or generally, or
All sorts of things, but that's what you're going to do.
yes, a sparse for me is like proportional to number of vertices, maybe n polylog n even. Okay, good. And in general, the graph may have n square edges, so I'm quadratically make my graph small. Okay. So the problem I'm interested in is this is written here. I can read this sequentially, and I spend memory proportional to n when I'm doing this. When it is finished, I made one pass over my input. Maybe I can solve the problem there. Maybe I don't have enough information. Then I'll go back and do this one more time. And my goal is to not use more than this much memory and not use too many passes over my input. Okay, I want to keep it as small as possible. Sounds good? Okay. And again, this is the formalization of the model that I wanted to talk about. It's not we are not going to even use any special power from streaming. Like the algorithm I'll tell you is a generic model-independent algorithm. And to just say one bit about motivation, think of picking a graph that fits your hard disk but doesn't fit your RAM, okay? You may have an algorithm, you can go on the internet and download an algorithm that solves maximum weight matching. It's not that easy to find one, but there are. So, and you can try to run it on your hard disk. It's really going to take a while, okay? Like if you make random access to your hard disk, it's really going to take forever, okay? But if you can do this thing and fit it inside your RAM, then in your RAM you can make random access. It's not going to take that long, okay? So the algorithm will become much, much faster. Okay, so that was for the motivation, etc. Any question here?
Is that true for solid state hard disk as well?
Say that again.
Is that true for solid state hard disk as well?
For what? I didn't.
You said the access will take a long time on hard disk. Is that true for solid state as well?
I don't know that. Probably. I think I'm happy I started with saying all I do is in TCS. So in theory, yes, but yes, good. All right, so let me now start talking about the algorithm, really. I wanted to get into the technical part right away. Okay, and I told you I want to show you everything, but what I'm going to tell you is supposed to work for non-bipartite and weighted graphs, okay? But I will start to talk about so that's somewhat the most general version of matching. I will start and talk about instead the simplest version, which is bipartite and unweighted, okay? And then at the end, I'll tell you actually everything that I'll tell you as it is will work for the general case also, okay? So for now, let's look at bipartite and unweighted. And let me tell you what is the algorithm. Okay, cool. So let me represent the algorithm in the spirit, for instance, that you may have seen algorithms like Clarkson's low-dimensional LP. If you've seen it, maybe this is the best way of stating the algorithm. Then I'll tell you can look at this algorithm a bit differently as well. But the algorithm is this. Suppose its input is a multigraph. For my purpose, it's going to matter that it's multigraph because I will apply it recursively and the graph will, even if you start from a graph, it will become a multigraph, okay? So let's say you have a multigraph and then you do the following. You sample, I guess we want actual number, 4n over epsilon edges, h from G. So you sample these many edges from G uniformly at random, okay? So this is a sparse, no? Like for me, think of epsilon as a constant, okay? So this is a sparse graph, I get. And I'm going to compute M and U as so I sampled my edges. I got something which is much sparser. And I now can go ahead and solve something like computationally heavy there. That thing is, I will find, let's say, 1 minus epsilon over 2, approximate matching and a vertex cover. This is a bipartite graph. These two problems are dual to each other. Okay? So I can solve both of them. I'll get a matching M which is larger than or equal to 1 minus epsilon over 2 times my vertex cover on the sparse graph. Okay? Good. Step 3.
Sorry, in step 2, you're computing both the matching and the vertex cover simultaneously?
Yes.
So return both of them.
Yes. You pick a primal-dual pair here. Okay? Good. So here, the only thing I know, M is larger than 1 minus epsilon over 2 times U. Okay, so now I have this.
Why don't you find the optimal one?
I can, actually, that's a very good point, and you can even find the optimal ones, but you can also just find this. This is easier to find, no? So this is better. If already this works, then you don't have to spend more time on finding an optimal matching, okay? And the reason I want to do this, eventually I'm going to get a 1 minus epsilon approximate solution. So I want to compare myself also with an oracle that only gives me a 1 minus epsilon approximate solution. Does this make sense? Okay. I'm not going to ask too much from my oracle. So I will do this. So step 3, like think of it like this. So you got this solution, and then you have the graph G in front of you. And you feel like maybe there were other edges that I should have picked that would have given me a better solution. So you sample a bunch of things, and you compute a solution from it. And you're not happy with this solution. This is not large enough. So you look at the original graph, and you check, are there edges there that if I have picked them, maybe I would have gotten a better solution? Does this make sense? Conceptually, even. The only thing you did in the first step was to sample a bunch of edges, okay? And now you're not happy with what you got. Then you want to say that, what should I have done instead, okay? And now that I talk about vertex cover, there is like a very good candidate. There are a bunch of edges that I should have tried to pick those. Do you know what are those edges?
Not covered by the cover?
Exactly. If there are edges that your cover is not covering, it seems like you did something wrong there, okay? So let's just do double reinsert all edges.
So this is a full tilt scan to step 3.
Step 3 is also a complete scan, yes.
So this is complete scan. The random sampling didn't have to be. You could have.
That's true. After one, yes, that's true. After one, like in the language of this streaming, this is one pass. Let's say this is another pass, okay? And eventually I'll get something which is asymptotic on the number of bounds. You're right. I mean, the factor 2 is not an easy thing to, like, but good. So, and the way I'll say this, I like to state it this way. This makes it very similar to Clarkson's low-dimensional LP. If you've not seen it, then maybe this doesn't make sense. So let me say again, what you do is that there are a bunch of edges that you have not covered. And let's say you have, this is a multigraph, okay? So maybe you have 5 copies of that edge. You put another 5 copies of that edge inside your graph, okay? So you make their you like double their numbers, okay? This is literally just to state it so that you don't bring in things like weight, etc. I'll have to actually bring in the notion of like weights here to talk about this a bit more naturally than, like in reality, even if you want to implement this thing, you don't do that. You don't copy an edge like 5 more times, okay? But does this make sense? This is the algorithm, and at this point you just say repeat, like from 1. So that's the entire algorithm. Good? Okay. So, any question? What is the algorithm? And the type of like analysis you would expect here is that if I'm not picking the right edges of my graph, I'll keep reinserting them back and back inside the graph, and eventually I flood this graph G that I have with edges of a maximum matching. Okay, I'll put so many edges of the maximum matching there that the only thing I can do is to sample those things. Okay, that's the type, roughly the type of analysis. Now we'll go and try to do it formally. Let's do we have another color? We don't. Okay. Let me just say that these things, it's a better way of looking at this. Maybe here. Maintain some importance. So maintain some number, some importance for every edge. QE is equal 1 initially. When you do the sampling, you can think of instead sampling each edge with probability QE divided by Q times 4n over epsilon. Q is summation of EQE. So all I'm doing is that instead of actually repeatedly putting the edges in the graph, which is weird, let's just maintain these numbers on each edge. This is the importance of that edge for me, okay? When I want to sample the edges, I sample each edge independently with such a probability, okay? And what I will do here, I'll just ignore the importances and just compute the matching vertex cover pair. And here, if an edge is not covered, I'll just make QE becomes 2 times QE. So that's the algorithm.
The algorithm ends whenever we cover it.
Good question. So let me show you that there is a fixed threshold. You do it a certain number of times, and then you just stop. Okay? And when you stop, and you're right, I mean, what you will say also will work, but I want to say that you will stop after a certain number of iterations. And when you stop, then you return the largest matching you ever found. Okay, you look at all the matchings that you found, you figure out which one is the largest one, and you return that. Okay? Good. Any question?
So we have to save all of those matchings.
Yes and no. I mean, you're just finding the largest one, so you can pick the largest one. It depends. There are things, though, like in a streaming, for instance, you cannot even annotate these things and update their weights. There, you have to maintain these U's instead of maintaining these things. Like, you don't have enough space to maintain this QE all the time. You only maintain the U values, and when an edge comes, you just count how many times it was not covered. You can calculate QE on the fly if you want. But that makes it a bit specific to the model. Don't worry about it. Like, this is the algorithm I want to analyze. Any question about this?
Your parameters are jumping out at me.
Okay.
You've chosen a multigraph of blue because it really works.
Yes.
However, you've done this, and you're picking O of n edges out of, let's say, n squared, or O of n theta of n squared. And it's a multigraph. So the way you do it, you happen to have it such that I think you're in the point where a constant number of edges will be taken multiple times, typically twice. Is that mathematically relevant?
Constant number of edges?
Yeah,
or?
the expectation. You're choosing n out of n squared objects.
Sure. So if you look at it this way, maybe now that we are bringing these things here, now it doesn't matter if it's a multi-graph or a graph. You can. So now this is a graph. So if you sample at this rate, each edge, then this is in expectation you are sampling 4n over epsilon.
Yeah, I get that too. It was the multi-graph jumping.
So then ignore that. Just let's do this thing. Okay.
So the final output will be the union of all the n's you find throughout the process?
The final output will be the largest matching that you find.
Oh, I see.
Okay, you return the largest one. Again, it will be fine even to return the last one, but I will not prove that. I will just show you that the largest one is good.
Do you have a specific algorithm in mind for computing, like in step 2?
This is just any off-the-shelf algorithm that solves approximate matching. Like you can use.
The running time is?
Their order m over epsilon for unweighted. You can do Hopcroft-Karp algorithm. If you want weighted, you do a scaling, and you lose log 1 over epsilon, and things like that. You can do this thing for non-bipartite matching as well. So this is a step you can do. And m here is the number of edges that you have, which is n over epsilon. So this step takes order n over epsilon square.
And one sort of silly question, from m to u, do you just like take both endpoints of all the edges in your map?
No. Then you will lose a factor too. This have to be a primal dual pair.
Okay.
Okay. Like all these algorithms find both of them at the same time. All right, good. So let's spend some time analyzing this algorithm. Now I'm going to, maybe I'll use this board also. So there are 3 steps in total. Step 1, so let's call them UT when you are computing it at time t. So this is the vertex cover you compute at time t. Okay, and this has, there are iterations here. So at tth iteration, let's call it UT. Okay, everything has a subscript, superscript. Okay, U of t is a vertex cover of your sample. Okay, by definition. Okay, but my question is how good it is in covering the edges of G itself. Okay. In a deterministic sense, the only thing I can say is that it covers every edge that is inside the edge, and maybe it doesn't do anything for the other edges. But I'm doing randomization, no? So I want to say some probabilistically, with a very good probability, now that I computed U over a sample, it's not like that my algorithm is like super tailored to this sample. It should do something non-trivial for the entire graph. Does that make sense? Like you sample, you pick a representation of your graph, you compute its vertex cover. This vertex cover should do something non-trivial for the entire graph itself, not just the sample. Okay? So the lemma is this. This is exponentially high probability, like 1 minus 2 to the omega n, minus omega n. U of t covers all but epsilon. What do I need as a constant? Let's write this. Let's look at the total weight of the edges that you have, total importances that you have. This U of t, even though it is only computed on a small sample, it still does a very good job at covering almost everything. Only roughly epsilon fraction of the edges of the entirety of G are not covered. Okay, so G had lots of edges. They were weighted, etc., or like have importances. I'm saying that when you do the sampling and you compute a vertex cover of the sample, you cover 1 minus epsilon fraction of all of G. Okay, so U of t is a by-criteria approximation to the vertex cover. It covers almost everything except for epsilon fraction. Does the statement make sense? This has a 1-line proof. Does someone see it? Maybe 2-line, but.
Are you saying that the size of the covers is increasing?
Not necessarily. It is true, but I'm not trying to say that here. It doesn't matter. This is not about size of the cover. Size of the cover is it's always smaller than the vertex cover of G because it's a subgraph. I'm saying that it does a good job in covering a lot of edges of G as well. Anyone wants to prove this, or should I do it? Okay, I leave this actually here. I'll come back to it if someone wants to think about it. It's really just 1 line. I'll show you the rest, and then I'll come back and prove it. So that's part A. And the only thing here is what is a corollary of this result? I haven't proved it. Maybe I can prove it in this much space later. Let me just write a corollary here. A corollary is that my total weights or total importances is growing slowly. It cannot grow very fast. Okay? After t iteration, it is at most 1 plus epsilon over 4 to the power t times m. Why is that? What is my update rule? If an edge is not covered, I double its importance. Okay? So from one iteration to the next iteration, this value increases by the weight of the edges not covered, by the importance of the edges not covered. Does that make sense? And that number is small. So in each iteration, you are increasing the importances at a slow rate. So you're not going to increase things very fast. Okay, that's it. Okay, good. So that's the corollary. What about the other part? The other lemma I need is that so what I want to say is that suppose I never found a large matching in my process. Okay? I want to say that my weights actually should increase a lot. Okay? So this is for all t less than or equal to some t. In part A, we prove that your total weights do not increase that much. In part B, we are saying that if you never find a large matching inside this algorithm, actually you have to increase QT by a lot. Okay, the last part is just to put these two things together, but let's prove this. Okay. This also has a short proof if someone wants to give it. That one is like elementary. This is not entirely elementary. It's a primal-dual analysis. So let me do this one. Okay. Let's define this vector y, which is 1 over t, summation of t equal 1 to t of u of t. By this I mean you've maintained you created a bunch of vertex cover, just take their average. Okay, create this vector y. This is a vector in 0, 1 to v. Okay, just take their average. And I want to say that y is something good is happening to y. Okay, so what do I know? My matching was never large enough. Okay, that means that MT, if MT is always that much, and I know that MT is always larger than 1 minus epsilon over 2 times UT, then if I put these two things together, I'll get that my UTs were also always smaller than 1 minus epsilon over 2 times that. So all the vertex covers that I found were small. I never found a very large vertex cover. I took their average. So y is a small vertex cover. I don't know whether it is a vertex cover or not, but at least I know sum of its value is small. Okay? So sum of value of y is less than 1 minus epsilon over 2 times opt. Good? Does this make sense? This is from the duality. MT was always a small. So that means that UT is always going to be a small. Okay? And y is their average. Now suppose this never happens. Okay? Then I want to claim that y is actually a vertex cover of your graph. Y is a fractional vertex cover of all of G. Does that make sense? Let's prove that. I can erase here. Are we happy with this? We are all happy with this. Then good. So y is a small. So we establish y is a small. Then let's say suppose this is not the case. okay? Or rather, suppose, what do I know? Okay, I want to say the following. If y is that much, I want to say that there exists some edge uv, such that yu plus yv has to be less than 1 minus epsilon over 2. My y cannot be a cover of my entire graph, okay? Why? Because if this doesn't exist, then it means that my y is covering all the edges this much. If I divide y by this number, I find a fractional vertex cover that covers all of my graph. And its value is less than opt. Okay, that cannot happen, no? I mean, I have the duality. My vertex cover should have value opt. So if there is an edge if there's no edge that my vertex cover does not cover enough, then y become an actual vertex cover of the entirety of G, okay? With a value which is too small. So that's a contradiction. So I know there is an edge that my y is not doing a good job covering, okay? What does this mean? This means that uv was not covered epsilon over 2t times. I mean, the y is just the average of these things, okay? So there is an edge that was not covered these many times. What does that mean? It means that I double its weight these many times. So the weight of that edge have went so high, which means the entire weight has gone so high also, okay? So I just used the simple primal dual analysis here. I just, again, going through this, we defined y. We said that if my MTs are always a small, my UTs are always a small. And if all UTs are a small, y is a small. If y cover every edge, I'll find a vertex cover of the entire graph which is too good to be true. Okay, so y cannot cover every edge. If it doesn't cover a particular edge, then it means that it didn't cover, like my process didn't cover this edge these many times. I double its weight so many times, the total weight becomes this much. Good? Okay. So how can I wrap these two things up? What does A plus B tell me? A plus B tells me this thing. At one end, Qt is less than 1 plus epsilon to the 4t times n. I also have Qt is more than 2 to the epsilon over 2 times t. I have both of these two things. Okay? Let's just see what does this. This is less than, I'm going to say 1 plus x is less than 2 to the 1.5x. So this is less than 2 to the 3 epsilon over 8t plus log m. Okay, just take my word for it. It's an inequality. Then this is true. I check in Wolfram alpha. Okay, good. So, no, I mean, this is easily seen to be true. Like, just put 0 and 1 there. Okay, anyway. And this thing is this much. If you just cancel these two with each other, this is going to tell you that t has to be less than 8 over epsilon log of n. So you have a very few number of iterations before you cannot satisfy both of these two simultaneously. Only log m over epsilon. Good. So if you run this algorithm, log m over epsilon time, 8 log m over epsilon time, one of your matchings have to become large enough. Good. In that language that we were talking before, it gives you a log m, order log m over epsilon past the streaming algorithm. Okay, good. It is randomized, but one thing I want to say is that it's not only with high probability. The probability that it fails is like 1 minus 2 to the minus omega n. It's not even 1 minus 1 over poly n. Okay, good. Any question about this? One thing to emphasize here that was important here, the dependence on epsilon is really small. It's like 1 over epsilon. It's not even 1 over epsilon a square. Why does that matter? Usually if you apply some sort of a boosting like this really looks like multiplicative weight. No, this is multiplicative weight. A typical boosting framework like this only gives you 1 over epsilon a square dependence. Okay, if you apply things like Plotkin-Shmoys-Tardos framework, you always get hit by 1 over epsilon a square factor. This time you are not. Okay, why? Because compared to a typical way of using multiplicative weight, you are extremely aggressive. Like, look at how like your update rule is a very aggressive update rule. You'll just double the weights. A typical learning rate in this type of no-regular algorithm is 1 plus epsilon. You take your steps very carefully. Here you are saying, no, just jump, like take a step of size 2, like double the weights. Okay? So that's one thing that gives you such a fast convergence in terms of epsilon. All right. I promise you I proved this thing. Anyone wants to say the proof now? Okay. It's unfair. I mean, if you've not done this type of things, it may sound fancy, but the way to prove it is to relax everything as much as you want. Like basically, let's prove. So just fix U, subset of, just fix any set of U, vertices, such that summation of E not covered by U, Q E of T is larger than epsilon 4 Q of T. I'm just looking at a subset of vertices that do not cover enough. And I'm just going to see what is the probability that I output this guy. Probability that UT is equal to U. So fix some subset. Is there a chance that I output it or not? Okay. The probability that I output it, I'm outputting a feasible vertex cover. Okay. So at the very least, U should be feasible for H. And the probability is over choice of H. So it's less than the probability that U is feasible for H. And now you may see what is happening. U does not cover so many edges. I'm picking my edges randomly, so it's quite likely that I pick enough things from here, which makes U infeasible. No? This probability is probability that E not covered. 1 minus QE over Q. What was I sampling? 4n over epsilon. Do I agree? The probability that what I get is feasible is very small. I should not sample any edges that will make this vertex cover infeasible. Okay, and I'm sampling my edges independently. This guy is less than 1 plus x is less than e to the x. I realized, so I said I'll do one line proof, and I'm just doing one line. Okay. For n over epsilon. Good. What is this summation? It's epsilon over 4q. No? If you cancel everything, this is x of minus n. So the probability that this u become feasible is e to the minus n. It's so small. Okay? So then what can I do? Just union bound over all choices of u. Like there are 2 to the n choices at most. So union bound over 2 to the n choices for u. Still, this probability is very, very small. Okay, so you don't have to do anything careful when you're proving this. Like this is the most brute force version, and it already works. Okay, so that's the entire proof of everything here. Question? How much more do I have? Oh, perfect. Okay. So I'll I'll tell you a couple of more things here. What did I prove? I only prove it for bipartite unweighted match. Okay. One thing also I have to emphasize, this algorithm, its runtime is not better than the runtime of a classical algorithm, okay? Its runtime is similar to that. That wasn't the point of this. The point was that a classical algorithm, when you just write m over epsilon, you don't actually take into account that m over epsilon, is it sequential m over epsilon over like the hard disk, for instance, or is it random access? If I give you an algorithm, I tell you its runtime is m over epsilon, and you're running it on your hard disk, you have no idea how long that it will take. Okay, that is, despite being purely theory person, that I've tried. That doesn't work. Okay, so, and you can run an exponential time algorithm like a SAT solver if your input fits into the RAM. The gap between RAM and hard is very different. Okay, so this algorithm does its runtime. If you just measure the runtime, is not any different. In fact, it has some additive terms that are worse. Okay, the point was that we wanted to run it in this particular model that only allowed me sequential access to my big part of the input. The only random access that I'm doing is on a much smaller part. Okay, I've never implemented this. I'm willing to bet it runs much faster than running this algorithm on the entire graph. Okay. Oh, I'm being recorded, and I think that's not a good idea, but it happens. All right, so let's do. So this was bipartite unweighted. Why that mattered really? Why can't I just do this entire thing for non-bipartite unweighted? Where do you think things start breaking?
Finding and matching and vertex cover at the same time.
Good. So yeah, so this is an NP-hard problem there, right there. But also, vertex cover was not the important thing. I have to find the primal-dual pair. The thing is that the dual of the non-bipartite matching is not vertex cover. I don't actually know the name for that. Is it like odd-set cover? So I know it as the dual of non-bipartite matching. Okay, so here you just have to pick a dual. So this part, the only change is that instead of picking vertex cover, you look at the LP and write the primal dual. Okay, so that part is fine. You have some weights, so the right thing to when you do the sampling is that you want to include the weights when you do the sampling as well. If you have an edge, its importance might be low, but its weight is higher, you want to actually multiply by the weights here. That's easy. Okay. If you want to do the analysis, this part actually, it really has nothing to do with vertex cover. This is a primal dual analysis. As it is, it will go through. Okay, and literally instead of writing yu plus yv, you write the dual values. It's the same thing. Nothing changes. There is one part here changes. Does anyone see? All of these things. Okay, this part changes. But do you see which step is the main part that is changing? Yeah.
In your probability there, you have to update with the weight that you.
So that's a good point. Yes. So you have to include weights and those things here. But fundamentally, something different is happening here. So you're not talking about vertex covers. You're talking about these duals. Okay. The dual of the matching is an object over 2 to the n variables. Okay. So if you do that, you can say that a fixed dual solution, you can do the same thing for it, and say that this fixed dual solution, you can actually bound it that it will go down with exponential probability. But then the number of duals are not 2 to the n. They are 2 to the 2 to the n. Okay? In fact, they are W. Number of duals are something like W to 2 to the n, where W is the maximum weight. You can't do union bound over it. Okay? But this is not a big deal at all. Do you know what is happening? So good. So here, this is the only time you want to do something a bit more like about matching theory. Like use one simple fact from matching theory. This is Cunningham-Marsh theorem. The optimal solutions to this dual form a laminar family. Okay? The only thing you need to know is that there are actually, yes, there are lots of duals, but the number of them that matters are at most something like this. There are these many real dual solutions. Okay? All your dual solutions form a laminar family. You can bound a number of them. If you are only doing your union bound over those things, that's enough to get the final answer. Okay? So this is the only time you want to look at the structure of the non-bipartite matching polytope, but you don't have to prove it. It just follows from this. You just have to bound a number of laminar family solutions. So the number you have is this much. You do union bound over this. This is not a large number. You only need to increase this by log n factor. Okay. If you do that, then the rest is the same. Okay. Sounds good?
So in your step 2 there, you've got an approximate version of the duality theorem. Is there an approximate version of the Cunningham-Marsh theorem?
Good. Yes, that is true. That's a very good point. Yes. Here, if you just, like a vanilla primal dual doesn't give you this, the algorithm of Petit and Randon actually returns, like the primal dual pairs that it returns are always, it's a laminar family of sets that it returns. Okay? So you can always say that the final solution you get out of this is a laminar family. Once you do that, you're union bounding only over laminar families, so that will go through. That's a very good point, that it doesn't follow as a black box primal dual pair. The underlying algorithm that you're using should satisfy that. Okay, but the existing algorithm do it. Okay. I don't know if this is also true as a black box statement, that if you give me any solution, I can make it into a laminar family also. Maybe even that's true. I have not thought about it. I don't know even if it's true or not. But you're right, but it is done by the current algorithms. Okay, good. So that's all I wanted to say, actually. Thank you very much.
Thank you for the talk. Questions?
So in step B, can you say that there are more edges not covered enough number of times and do better with the analysis?
Okay, that's a very good point. So, what Lapchi is saying is that this analysis is very simplified in the sense that you're just saying, oh, one edge is not covered, and so it increases the weights that much. You can say you can tolerate up to epsilon n edges not being covered, or epsilon opt edges not being covered, because that's fine. No, you want a 1 minus epsilon approximate matching or vertex cover. If you're not covering that many edges, that's okay. So you can throw in an epsilon n factor here. When you go through these things, it will reduce this bound. Instead of log m, I will write here. You can reduce it to log of m over epsilon n over epsilon. So this may be order of that. Okay. Unfortunately, it doesn't matter that much, because usually you are interested in reducing, like you are interested in cases when m is sufficiently large. Okay, but yes, if m is n polylog n, then it becomes log n, etc. To me, the most interesting case of this is when m is n a square. Okay, so it doesn't buy you that much. Okay. You can do that if you are solving this was trying to solve the dual, And the dual, the problem is like the number of variables you have. Like there are epsilon n variables among m, many of them. If you solve the primal, not using this algorithm, you can get rid of this and make it log 1 or epsilon, but then you'll get hit by epsilon square. Okay, so you can do this type of analysis, increase this to epsilon square and get hit here. Sorry, improve this, but get hit here by another 1 or epsilon factor.
Sorry, was it it?
Yes.
Any further questions? Thank you. There are no questions.